Are you able? Okay, are you able to share your screen, Elette?
Hi, let's take a look.
Okay. Perfect. Very good.
Excellent.
Okay, so let's see. So our next speaker is Elette Boyle from IDC Ercilia and NTT Research. So thank you, Elette, for coming to speak. Looking forward to the talk. And yeah, we're going to hear about Sublinear GMW-Style compilers. So Elette, the floor is yours.
All right, thanks very much. Happy to be speaking here. So indeed, I'll be talking about Sublinear GMW-style compilers for MPC with preprocessing. You'll see what all of this bundle of things means throughout the talk. And I'm going to be talking a little bit of a mix of a survey and diving a little bit deeper into part of it. But this is based on a couple of works. First of all, one together with Dan Bonnet, Henry Corrigan-Gibbs, Niv Yoboa, and Yuval Ishai. And then a small line of work together with Niv Yuval and Ariel Nov. Okay, so let me start by trying to unpack this title a little bit. So we have MPC, we have GMW-style compilers and so forth. So for those of non-cryptographers out in the crowd, or if you haven't heard, so secure multi-party computation, or MPC, which is the focus of this talk, is a cryptographic notion where you have a collection of parties who want to jointly compute on secret data without revealing this data. Okay, so more concretely, suppose you have some collection of parties, each with some secret inputs. And an MPC protocol is a way that kind of dictates how these parties will communicate back and forth, such that for some public function F, at the conclusion of this protocol, everybody will learn F applied globally across all these secret inputs. But the interesting thing is that nothing else is revealed about the inputs. And this is true even given some subset of parties who might be acting adversarially. And the adversarial actions here are really going to be the focus of today. So a little bit more concretely here, what is the adversarial model that's considered? It was an entire spectrum of different things. But roughly, there's two kind of main categories of settings that lead to very different structures and types of protocols. And that has to do with whether you assume there's a majority of these parties who are acting honestly or not. Okay, so not the honest majority case, here it turns out you can actually get information theoretic security without making any cryptographic hardness assumptions. And part of this, if you sort of zoom in or open up what are the tools that are used, there's a lot of this sort of error correcting codes or Shamir secret sharing that allows you to compute on shares of secrets that are somehow kind of held robustly across these parties. And this robustness is going to return over and over again. In contrast, for a dishonest majority, for example, here, if you just have two parties, or if you have more parties, but you're not guaranteed a strict honest majority, then it turns out that this requires public key cryptography in order to achieve. And often because of that, so if you look, for example, in any spectrum of kind of practical MPC protocols, what you end up doing in this setting is splitting the protocol into two parts, which kind of allows you to, in a sense, push the cryptography, these heavy public key cryptography steps, to an offline pre-processing phase. So this will be something that you're kind of allowed communication and computation. But in this phase, the inputs are not known. So this whole phase needs to be input independent. And the benefit of this, and I'll talk more about it later on, is that then once the inputs do come along, it's possible to achieve a very cheap and sort of non-cryptographic online phase, which can be formalized. Okay, so what are these now GMW-style compilers? Okay, so across both of these spectrums, if you're looking at honest majority or dishonest majority, you can still ask, okay, what is the action of adversarial parties? And ever since the kind of the original works back in the 1980s, building MPC protocols, the standard structure of designing protocols is to first build one with a weaker form of passive security, Okay, so here these in this setting you prove it's secure, assuming that even the adversarial parties are following the protocol, and what they're doing to kind of cheat is that they're combining information together that they're not supposed to. Okay, so this is an easier goal to achieve. And then going from there all the way up to kind of the ultimate goal, which is standard active security. Active in the sense that now the adversarial parties can actively try to cheat in the protocol, send bad messages, and do whatever they can to ruin the lives of the honest parties. Okay, and in this step, this arrow up is some form of compiler. And the original such one was in these works of Goldreich, Micali, and Vigdorsen, which used a tool of zero knowledge to roughly force passive behavior, to kind of force everybody to, once they do an action, to prove that this is indeed the correct action they were supposed to do. Okay, so these are this allows you to reduce the security given this extra layer on top. Okay, and so this arrow is itself a big area of research. There's been a lot of different approaches and different techniques in order to do this passive to active security compilers. And it's still a really interesting and important area of research, really where the goal is to try to minimize the overhead of this arrow going up. And when I refer to the overhead, of course, there's different metrics. The one I'm going to be focusing on is the communication complexity. So of course, also the computation plays a role. It ends up being the case, and at least in a lot of these protocols, communication ends up being a bottleneck. Okay, so before kind of anything else, a little bit of a high-level overview. So suppose I'm in general want to securely compute some function f. What is the communication complexity of solutions that we have for this? And in theory, it's very, very small. So in theory, meaning that, after some breakthrough work, which certainly you've probably heard about in fully homomorphic encryption, it turns out that there are ways of doing secure computation where I really just kind of have to send an encryption of say, my inputs and get encryptions of the outputs back. So the communication is very small compared to a potentially large function f. Okay, so I wrote this as in theory because these indeed are beautiful theoretical results. But in some sense, despite a lot of amazing progress in optimizing these things, at the end of the day, they're based on relatively heavy cryptographic tools, so fully homomorphic encryption or so forth. And this puts a lot of limitations in terms of the practical feasibility of these things. So for example, even though the complexity asymptotically is very, very small, if you open up what this big O notation is, concretely, the actual concrete communication here ends up being maybe orders of magnitude larger. Okay, so for whatever reason, in any case, I'm going to be focusing on the second category. And here, so how can I kind of distinguish these from a theoretical standpoint? For example, suppose that in terms of cryptographic assumptions, I'm only going to allow you to use a black box use of a pseudorandom generator. At least if I'm talking about preprocessing, don't worry, I'll get to that later. I mean, in the online portion. Okay, so in any case, this is the regime where practical protocols exist. And in this regime, so again, there's been, tremendous amount of work since the 1980s, getting these protocols more and more efficient and down and less overheads. And roughly what we have is that for this category of protocols, the communication complexity scales here as some constant alpha times the circuit size representation of the function f. Okay, so here alpha is some small constant greater than or equal to 2 in general. And this alpha I'm going to carry throughout the talk on and off a little bit. So again, this just represents kind of the elements per party, where the elements are either, say, bits, if we're talking about a representation of the function as a Boolean circuit, or whatever arithmetic structure you have, if f is arithmetic. Okay, so as I mentioned, there's a long line of work improving this constant alpha. And what I want to sort of direct your attention to is that there's a gap, or at least there was a gap, between this alpha that could be achieved in this lower, weaker passive security level versus that which could be achieved in active security. And here, from prior work, kind of combining everything together, the cost of this step was at least twice the amount of communication. And in some cases, as you'll see, even significantly more. Okay, so now kind of combining everything together, the goal of let's say this work, or this collection of works, is to perform this passive to active security compilation with sublinear additive overhead in the communication. Here, sublinear, I'm thinking of the leading term, is the circuit size representation of the function to be computed. And what that means in terms of these alphas floating around is that if you have such a compiler, then whatever this alpha is that parties are communicating per gate, then in an amortized sense, at least amortized over the circuit size, you have essentially the same alpha for the actively secure protocol. Okay, and as you might guess, this is precisely what we're able to achieve. Okay, so the punchline of this talk, which is going to, again, kind of smear over a couple of different works, is a collection of different sublinear additive communication passive to active MPC compilers. And maybe the core technique that brings all of these things together, and I think is kind of an exciting thing that has a lot more to be leveraged from, is a tool that we refer to as zero knowledge on distributed data. Okay, so I said that there's a collection of different works with such compilers. And previously, in the last few years, we've been able to use this tool to get low communication passive to active compilers in the setting of honest majority. And some of the new and particularly exciting results, in my opinion, are some very fresh results showing how you can actually do this in the dishonest majority setting as well. And as we'll see, actually, this came, at least to us, as a little bit of a surprise that this could be useful. Okay, so for the remainder of the talk, what I would like to do, so I'll talk a little bit about this tool, first of all, this notion of zero knowledge on distributed data. And I'll give you, I want to give a little bit of a survey also, a bit of what are the high-level frameworks of how can you use this tool to achieve passive to active compilers in MPC. And it's not just a one sort of approach, but there's at least two different high-level approaches that we've already identified, and quite possible that there's many more. Okay, and then I'll talk about what does this mean? How does this translate to actual concrete results for MPC compilers? And I'll be focusing on these new results in the dishonest majority setting. I guess, actually, I'm not sure if we're stopping for questions. So maybe I'll leave questions to the end in any case.
Yeah, we can do that. We can take the questions at the end.
Okay, great. Okay, so proceeding forth. So let me tell you about this zero knowledge on distributed data. Okay, as you've probably seen before, the notion of zero knowledge, the original notion, is a setting with a prover and a verifier who each know some input X. Okay, and the prover would like to prove to the verifier that X is a member of some language L. Okay, and we say that this protocol of going back and forth is zero knowledge if at the conclusion of the protocol, the verifier learns nothing beyond what he knew already, which includes in particular the statement X, and this new bit of information that X is a member of the language L. Okay, so zero knowledge on distributed data is a notion put forth together in this work with Dan Henry Niven-Yuval a couple years ago. And here, this image is a little bit split, okay? Where instead of having a single verifier who holds the entire input X, we now consider a setting with potentially multiple verifiers who are holding pieces of this statement, okay? And these pieces can be one of a few different things. Okay, they could be, for example, additive secret shares or some linear secret shares of parts of X. They can also just be, actual pieces, like maybe verifier number 1 knows the first symbols of X, verifier number 2 knows the second symbols, and so forth. Okay, and more generally, what we need is that there's some sort of linear expression that combines what's being held by the different verifiers to reconstruct the statement X. Okay, so in more detail. Okay, so such a protocol has the prover who has the whole statement X and who communicates information to the verifiers. Okay, and sort of in the simplistic version of this, you can think of the prover just sending a proof or pieces of a proof to the verifiers. Okay, then the verifiers will communicate amongst themselves and ultimately decide to accept or reject the prover. Completeness means that if the prover is really honest and X is truly in the language, then the prover will be accepted. Zero knowledge here says something sort of the natural extension of standard zero knowledge. Okay, but note that here that the zero knowledge, as usual, says that the verifiers learn nothing more than they knew, together with the fact that X is in the language. And here I want to focus on this. In the standard setting, the verifier knew X in entirety. So that was okay. You could, reveal X and it didn't mean anything. Here, this is not the case, okay? And zero knowledge is going to demand even stronger the property that even if you have a collection of corrupt verifiers, here this verifiers VI in the set S, they should learn nothing beyond the fact that X is in the language, whatever this combined X is. And in fact, they should not learn anything else about X beyond these pieces Xi that they already knew. Okay, so this is an important property that will be quite useful. And soundness, so if you have, suppose that you have a corrupt prover, but that the verifiers are honest, okay, then soundness is somewhat straightforward. It says that if an honest verifier accepts, then it must be that X is in the language. And things get a little bit more tricky though, when you have a potential case where a prover and verifiers could be colluding together. Okay, so it's a little bit more subtle. I'm not going to go into the fine details there, but I will point out that one extra thing that's necessary in that case is that that we can't handle sort of general splits of statements X across the verifiers, but to have kind of an achievable and interesting notion of soundness here, what we require is that whatever these Xi's are that are being held by the verifiers, that there's some sort of robust encoding of the entire input X. Okay, in the sense that if you take just the Xi's held by the honest verifiers, that's already enough information to determine X. Okay, so this kind of ties cheating verifiers to not be able to switch the input that's being proved on. Okay, so this is the new notion. I'm going to occasionally refer to this as DZK in my slides. I should mention that distributed things and zero knowledge is a somewhat minefield of notations. And then we point out two related sounding, at least, but different notions that are out in the literature. So one referred to as distributed zero knowledge and other related works. They consider a different goal where they take the prover, or say you could also consider the verifier, but distributing for purposes of efficiency. So here, this is not the case where, for example, the verifiers need to have zero knowledge, even with their pieces of the statement and so forth. And another notion, which also considers a split verifier, is this line of work relating to interactive distributed proofs. Actually, is also quite an interesting line of work, but in their model, it's a bit of a different setting. The verifiers are on some sort of communication graph, and the statement that the prover is proving relates to properties of the graph. So it's a little bit more of a targeted thing, and it's a bit different from what we're talking about. Okay, so back to what we are talking about. Again, DZK, this is zero knowledge on distributed data. Just a couple remarks about this new notion. One thing is that because the verifiers don't actually know X, this shifts a little bit of the interesting regime from what we're used to. So for example, even if I have a very simple language L, something that if the verifier knew the statement, knew the input X, could simply check it himself. In this case, this is no longer possible, okay, because maybe it only knows one piece of X and it needs the other pieces in order to perform this simple computation. And because of this, and because of sort of interesting applications of this new notion, there's going to be some different complexity goals than maybe in other application settings. And in particular, one thing is that we're going to care a lot about the proof size, or kind of in turn, the communication that the prover is sending to the verifiers. And of course, this is probably pretty natural or expected, given the fact that I want to use these in MPC protocols and I don't want to incur much communication. Okay, I have one slide here, just a little bit about building these protocols. This is not the focus of this talk. This could be a whole nother talk on its own. And in fact, I will tease you without saying much about another very interesting notion that we came up with and built on the pathway to building these distributed zero knowledge on distributed data protocols. Which is a notion of what we call fully linear PCPs, probabilistically checkable proofs, and IOPs, which are interactive oracle proofs. So just one sentence about these things. If you're familiar with PCPs or PCPs of proximity or linear PCPs, okay, it's kind of a combination of those three things. Where loosely you can view this as, so a prover here will kind of commit to some proof pi. The input you can think about as written next to it. And the verifier here will have access to linear queries on the combination of the input and the proof together. So this kind of puts it, it's like, as I said, it's sort of a combination of these other three notions. It turns out that this is really in line exactly with these protocols that we're after. And in fact, you can show a clean generic transformation that if you build a fully linear PCP or IOP of this form, then you can directly transform that into a zero knowledge protocol for proofs on distributed data. Okay, so again, I'm not going to say much more than that about this object. I will say that it turns out that these fully linear PCPs actually exist implicitly in the literature. For our setting, we wanted to build a new version to get us some nice properties. And we did so in this work. This is the 2019 crypto work, Bonnet et al. Of all of us, building on ideas of the sum check protocol. Okay, so kind of the takeaway that I want you to remember for this slide is that for simple languages, okay, we're referring to simple languages as low degree that I can verify given the statement X. There exists some low degree polynomial of the pieces of X that evaluates, say, to 0 if this thing is in the language or not. Okay, and so this is the one part that we have simple low degree statements. The second is that the proof size, okay, is sublinear in the statement size. So here are some input X, has length N, it's N field elements. And the size of our proofs, if you need a one shot, we're able to do this in square roots, roughly square root the statement size. For degree 2, and more generally, if you allow rounds of interaction, so this one comes from the interactive oracle proof instead of the PCP, then you can actually crank this proof size down via recursion to only logarithmic in the size of X. Okay, two different remarks here. First of all, there's no computational assumptions in this theorem because none are required. So these are purely information theoretic statements. And the second here, so kind of drawing your attention maybe to this error term. So indeed, each of these have some cheating possibility of 1 over the field size. If your field size is large, that's fantastic. If your field size is small, that kind of sucks, but don't worry. Because you can crank this down as well by doing this proof over some sort of extension. Okay, so maybe this statement is jumping ahead a little bit, but yeah, okay, it is jumping ahead. So don't worry, even if your original statement, say, was over bits, then you can run this proof by embedding into a field extension, for example, and you can get very small error. Okay, so this concludes what I wanted to say about this notion of zero knowledge on distributed data. And now I want to show you a bit about how we've been able to take this tool and use it to derive these compilers of going from passive security all the way up to active security. Okay, and let me start with a very high level kind of bird's eye view plan of what's going to go on. Okay, so remember, this is a compiler. We're starting with some protocol that's only passively secure. Okay, and indeed, these compilers actually don't just broadly apply to all protocols, but they'll apply to passively secure protocols with some useful natural structure. Because of the venue of this talk and the length of time, I'm going to sort of smear my hand about what is this natural structure. But perhaps one thing I will say about it is that, it looks like this. So this is at least one thing that we want from it, is that the underlying passively secure protocol can be split into two parts. So one is the bulk of the protocol, everything here pi prime except for the final message. And the final message itself is the final part of the protocol. And so one thing that this hasn't really said anything about structure. So one assumption that we have, which happens to hold for essentially all natural passively secure protocols that have been designed, is that up until this very final message, even if you cheat, you don't learn anything. Okay, so kind of everything at the very beginning, this pi prime light gray part, even if you're being a malicious agent, then everything you're seeing just looks like random garbage up until the final message. And the final message is when everything that you see now suddenly becomes clear, and it allows you to kind of convert this to what should the function output be. Okay, so given this structure, perhaps it's very natural that what we really want to do here is kind of squeeze in an extra phase in between these two parts to somehow prove in zero knowledge that pi prime was performed correctly. Okay, so if we can do that, if it was performed correctly, then that means it's going to be safe to exchange this final message. And if not, then you'll get caught. Hopefully this is the goal. And if any party rejects from this proof, then you'll simply abort the protocol. Okay, so everything I'm talking about, okay, not everything, some of the results also give you guaranteed output delivery, but let me just focus on security with abort. Okay, so this is the high level plan, and I want to give you two high level kind of types or compiler frameworks. The first, which I refer to as type 1, is that at the conclusion of pi prime, each party will act as prover in one of these zero knowledge proofs on distributed data protocols. And it will prove to the other parties, will act as verifiers, that it performed its messages in pi prime correctly. Okay, so let's take a look here. What is the input that's being proved? Is going to be the collection, the concatenation of all of the incoming and outgoing messages that were sent or received to this party by anybody else in the first part of the protocol. Okay. And what do the different verifier parties know about this? Well, each other party knows exactly its subset of those messages that came to or from that party. Okay, so for example, here X1, this corresponds to the piece of X that were the messages going back and forth on these communication lines and so forth. Okay, so what do we need to check? Well, now it's kind of opening up and seeing what was he supposed to do in this first protocol pi prime. Okay, and when you look at natural protocols, what this boils down to is that in each step of the protocol, it gets some messages in and is supposed to perform some degree to computation and send corresponding messages out. What that means is that to verify that this party's messages were performed correctly, that is, he acted honestly, or at least semi-honestly, passive adversary, that is, in the first part of the protocol, is some degree to relation on this collection of incoming and outgoing messages. And this is perfect, okay? Because these degree two, this is exactly a form of simple relation that we have sublinear size proofs for. Okay, so this is the first type of protocol. And one comment here about the soundness. So as I mentioned, soundness, if I just run this thing totally out of the box, then soundness is 1 over the field size, where the field size is whatever these messages were. Okay, and that ends up being, if we were computing a Boolean circuit, these messages are bits. And if we were computing an arithmetic circuit, these messages will be whatever these field elements are. Okay, so this, this seems like a potential danger point, because indeed soundness error 1 over 2 is not so appealing for these protocols. And now this is where I want to remind you of this comment that I had before, that you can amplify the proof itself, okay, embedding the proof part into a larger space. And the point to point out is that this does not affect the communication of pi prime, of everything that happened up till this. That's exactly as it was before. And the only thing that gets a little bit bloated is the communication for this proving phase, the part that was in the blue bubble in the previous slide. Okay, and since this proving phase was already communication sublinear in the circuit size, then the fact that we get a little bit of bloat here is not enough to push it to be too big. So it's going to remain sublinear in the circuit size. Okay, so again, this type 1 compiler had each party individually act as a prover to the other parties to prove that its actions were done honestly. Okay, and of course this can be, everybody can prove in parallel. So looking at applications of this type 1 compiler, it's perfect for 3 parties with 1 corruption. It's exactly what you need. This is this we had in this original work here. And what's really nice and kind of simple about that setting is that either the prover or a verifier can be corrupt, because there's only 1 corrupt party. Turns out that if you have n parties and t corruptions, so as long as I'm maintaining here, this is honest majority, like a strict honest majority, but it's more than 1 corruption, then things become a little bit more tricky. And the reason is because you now have this issue where if a prover could potentially collude with verifiers, you need to make sure that you have this robustness of encoding of the statement of the input X. And this ends up taking a little bit of work. It turns out actually we can still get type 1 compiler to work in this setting, but that only came about a little bit later. But because of this challenge in the original work and follow-ups, this kind of led us to build a different type of compiler. Okay, and this is, I'm going to refer to as type 2. So in contrast to type 1, where each party proved to everybody else in parallel, In this case, what will happen is that all of the parties together will jointly emulate a single prover that will prove not about the individual messages, but instead prove that secret shared wire values are consistent. Okay, so let me step through this a little bit more with the picture. Okay, so the statement is going to be formed by a collection of basically secret shares. Okay, so these are these classes of protocols where for every wire of the circuit being computed, essentially the parties compute some form of secret shares of what is the payload that should really be on this wire given our secret inputs. Okay, so take the whole circuit and think about it. For every wire, you have a set of these secret shares. This combined set of secret shares, sticking them all together, this is the new giant input that we want to prove something about. Okay, and note that unlike before, nobody knows the whole statement, the whole X itself. Okay, because each party only knows one of the secret shares of each of these sets of secret shares. Okay, so this is why no party can individually act as prover on his own, but instead the parties will perform kind of a small scale secure computation to execute the actions of the prover, even though everybody only knows pieces of what the prover should know. Okay, so so the good news of all of this is that, again, the statement, like the language or relation that we want to prove on this giant combined set of secret shares is again very simple. Okay, and here you can kind of see what is it going to be. It's some form of, if I were to combine these shares, which typically is a linear operation, that's equal to the product of what I would get if I combine these shares multiplied by what I get when I combine these shares. Okay, and I have sort of one of these statements for each and every multiplication gate. These turn out to be the challenging ones. Okay, so I can express this as one giant degree 2 constraint that has lots and lots of subchecks within it. Okay, and so this one is the fact that this is degree 2 and not constant degree in this case, in this type 2 compiler, is very important. So the previous one, it was nice, but any constant degree would sort of do the job. And here in this compiler, it's actually very important that this is a degree 2 relation. And the reason for that is that if you open up actually the code of what the prover is supposed to do in these protocols, in order to prove a degree 2 relation, the prover itself takes an action that is a degree 2 operation. And what that means is that we can actually sort of perform this prover computation, which, by the way, is taking this huge statement as an input, but has a small output, which is the size of the sublinear size proof. And we can perform this degree 2 kind of compression securely without interaction. And this allows us to not have this huge overhead of communication, because if we were trying to securely like jointly emulate the prover without this trick, then we would have to communicate like the input size, which is very large. Okay, so this is the second type of compiler, and this appears in different kind of sets of works here. Okay, yeah, I see as per standard, I'm running a little bit slow. So let me just kind of quickly, I won't get into this slide. The whole point of this slide is to talk about, kind of excitedly, the results that we were able to get in the honest majority setting. And the punchline here, if you recall, this alpha was a metric of the communication cost that you needed. So you want alpha as small as possible. And comparing against prior works, you can see that now for using these techniques that we can get alpha down to much, much lower than we were able to do. And this is a relatively optimized space. So any kind of multiplicative factor here is pretty exciting. Actually, another thing that I didn't make a big enough point about, I kept talking about fields, but our works also hold over rings of the form Zn. So this is kind of a nice thing where typically in MPC, like everything, you assume it's some sort of finite field. And then if you want something over a ring structure, you typically have to work very, very hard to make sure that that's going to be okay. And sort of as an added benefit here, we get these, because this zero knowledge over distributed data machinery automatically works over rings of the form Zn in addition to any field, we get these things without any extra work, which I always enjoy. Okay, so in my remaining very short period of time, let me hopefully get to what I wanted to talk about, which is what about the case of dishonest majority? And let me start by saying, wait a second, what can we do here? There seems to be a problem, okay? And the problem is that as soon as we had more than one corruption, it was really important that whatever this X is that's being proved was held robustly across the parties. Okay, so we know that we have some sort of secret sharing of these things, but the robustness meant that we wanted it to be that X could be recovered just by the shares of honest parties. Okay, but if you have a dishonest majority, for example, suppose you just have two parties here, this seems like something that's impossible. Okay, if I'm secret sharing something across two parties, I cannot require that just a single honest party can recover the statement. Okay, so don't panic. This is going to be possible, and I see from the fact that Amit and Dan are putting the video on, I'm not going to get very far into here. So let me actually. How many minutes do I have? 0 minutes.
Well, we want to leave some time for questions.
I see. Okay.
But maybe you can tell maybe you could say kind of the punchline of the technique, and then go to the conclusion slide.
Yeah. So okay, that sounds fair. So let me just say the following then. So this is going back to this model of MPC with preprocessing. Remember where there was an offline phase and an online phase. So the offline is input independent, and the online phase can be done very cheaply. And this offline part, so this is, you can kind of study this in an intermediate setting where you view this as some correlated randomness that some dealer comes and gives you. Okay, just sort of zoom forward and say that the important metrics, or some of the very important metrics of such protocols, are how much of this preprocessing do you need? And also, what is the communication in the online phase? Okay, so I'll just say that what we're able to achieve, and still I'm keeping it as a tease, I suppose, of how this is done, is that we're able to get both of these being sublinear additive overhead in both the online communication, so just a little bit of extra communication here, and in the offline preprocessing, which is not something that we knew how to do before, that always at least one of these two had to be linear overhead. And this holds for protocols in the preprocessing model with certain properties. I'm not going to get into the details of that. And so let me just close it with a picture, I suppose, and then go to conclusions, where I do want to say, what is the punchline? Punchline, how do we deal with this conundrum of the robust sharing? And the idea of this work is that we can actually treat the dealer, whoever's generating this sort of correlated randomness, as an honest party in the execution. And what do we mean? What that sort of means is that you'll think the preprocessing correlation is going to consist essentially of what would the actions be of an additional party in the protocol. But in this case, it's guaranteed to be honest, okay? Because the preprocessing is assumed to be honest. And this is sort of enforced by actually running a secure protocol for the preprocessing. Okay, so this star sharing, I'm not going to tell you what it is. I'm just going to put it out there. But essentially means that even though now, so unlike Shamir secret shares where you had robustness of encoding secret values, here it could be that all the parties but one are corrupt. But because the dealer is guaranteed to be honest, you always have some sort of form of robustness where the honest party together with the dealer have shares that allow you to reconstruct. Okay, and this is not immediate. There's a lot of tricky things that you have to deal with. For example, the dealer is not a party, right? The dealer is generating something before he knows what the inputs are. So somehow you have to sort of maneuver your protocol so that whatever this one party would be doing in the online phase is totally independent of the inputs. And you can kind of force this to be true with some trickery. Okay, so there's a recent work where we show how to emulate this dealer in even more exciting of ways, but I've overstayed my welcome. So unless somebody asks a question about that, I'll keep it to this. So in conclusion, I've described to you this notion of distributed knowledge on this, zero knowledge on distributed data, and a collection of ways for using this for passive to active MPC compilers. And let me just leave it that there's a lot of really interesting open directions still to follow there, including trying to increase generality, different types of base protocols, things, for example, based on garbled circuits. We have no idea how to approach this. And the thing that I didn't talk about is kind of an exciting thing, actually, that in this dishonest majority setting, so we have a way now of basically putting the entire pre-processing protocol of securely generating this pre-processing and everything with sublinear communication. So it's like a speeds type protocol for those who know what this means, but the entire pre-processing is sublinear communication. And we can do this just with additively homomorphic encryption. With this, I will conclude.
Great, thank you so much, Elette. This is wonderful. So I have to say, like, well, I think one important comment here is that this is not just asymptotically good. This is like these constructions are actually very practical and they're very actually competitive. Actually, they're probably the best ways to run MPC these days.
Yes, and I think what's really cool is that there's so much potential also. Like, we've really been in this recent work, we've been trying to see, really, can we push the concrete efficiency of these things beyond
actually, that's what I was going to ask. So concretely, how does it compare to so speeds is kind of the previous standard way to deal with dishonest majority. So how does concretely this compares to the speeds method?
So in comparison, the online portion is about the same. We have a little bit more computation cost. But in comparison, the offline, we can, so I'll just say kind of roughly for speeds and such. So you need these authenticated beaver triples. Sorry for those who don't know what this means, but the cost of generating those ends up being quite expensive. And roughly what we can do is we can do it just with the semi-honest triples, plus a little bit of stuff on top, which is using this additively homomorphic encryption, but in sublinear amounts kind of this. And this is fantastic. So the additively homomorphic encryption part is sublinear. And because we only need the semi-honest beaver triples, we can leverage this machinery that allows us to completely kind of compress the communication of that using pseudo-random correlation generators, this like silent OT style thing. So it's kind of cool. Actually, it combines a couple different lines of work I've been a part of. So it's really cool, really exciting for me.
Yeah, very nice. I guess it's a good message from this talk that actually, if we need dishonest majority MPC, now your paper is kind of the place to look up how to do that.
Indeed.
Yeah. So fantastic. So wonderful. Thank you so much, Elette. So let's see. Are there any other? Maybe we could take one more question, and then I think we need to break so people can make it to the next session in Fox. So any other questions from the audience? No, everybody seems quite happy. Ron has a question. Ron, please go ahead. Oh, no, you just turned on your video.
No.
I see. Okay. Ron has more philosophical questions, but that we can leave maybe to the break.
Having a video just to thank you to Elette. Yeah, thank you.
Yeah.
Great.
You're very welcome.
Okay, sounds great. So with that, thank you again, Elette. Wonderful talk. And so I guess with that, we'll conclude the first session of the crypto workshop. we'll see you again this afternoon, and then also tomorrow morning, and well, I guess my time, tomorrow morning and tomorrow afternoon. So